All right, guys, here's question 3 from the chapter 9 through 10 free response. So we've got, in this scenario, we've got a spring attached to a glider on an air track with a photo gate in the middle of this thing that's going to measure the velocity as it comes through that section. All right, so part A, assuming no energy is lost, write the equation for the conservation of mechanical energy that would apply to this situation. All right, so here's what we need to remember. In this situation, when it says conservation, we can think that this represents a change of energy, all right? Now, for this scenario, we're looking at the change of mechanical energy. And since it's being conserved, the change of mechanical energy should be equal to 0 here, okay? Now, if we think of what is mechanical energy, well, mechanical energy is potential energy plus kinetic energy. So these quantities should not change throughout this, all right? So if we think about the energies that are at this location right here, I've got potential energy in the spring, and then at this location right here, I've got kinetic energy. So all I can say here is that the kinetic energy is going to be equal to the potential energy in the spring because I'm not losing any energy here because this is on an air track, so there's no friction, there's no dissipative forces. All of my energy is being converted from kinetic to potential energy in the spring and vice versa, all right? Now, kinetic energy is 1/2 mv squared. Potential energy is in the spring is 1/2 kx squared. Now, this is where some of us miss points. It wants you to plug in k equals 40 Newton meters, so you get the answer of 1/2 mv squared is equal to 1/2 times 40 x squared. All right, so in this problem, 1 point was associated with this statement, and then 1 point was associated with that statement for a total of 2. So just remember, always plug in information that they give you. Here, that information was k. All right, on the plot below, plot b squared versus x squared, label the axes, including units and scale. Graphs are the easiest places to get points, guys. There are 3 total points on this problem. 2 out of 3 of those come from simply labeling your axes, including units, and making a linear scale on each section. So let's get into what that means now. In the data table, we are given data for x squared and velocity squared. It says v squared versus x squared, so I'm going to put v squared on this axis and x squared on this axis. If you had plotted x squared versus v squared, that would have been fine. But in general, if it says v squared versus x squared, think y versus x. That's just usually how I approach it. Notice I put a times 10 to the negative 2 on the x-axis. That's just going to make my life easier when I'm making this scale up, all right? So v squared goes all the way to nearly 5, so I'm just going to count by ones, 1, 2, 3, 4, 5. And then extension squared goes from 0.09 to 2.3, so I'm just going to go up by 0.5s here. 0.5, 1, 1.5, 2, 2.5. And now I can just plot these points. So the first point is 0.09 and 0.22. So come down here. 0.09, 0.22 is probably going to be somewhere in here. Then we've got 0.36 and 0.76. So 0.36 and 0.76 right there. We got 0.81 and 1.7. So we got 0.81 and 1.7. Should be about there. Then 1.4 and 2.6. Right there. And finally 2.3 and 4.8. Right there. All right. So on this one, the points come from the axes, linear scale, and then your correct points. So if you plotted the points correctly, if you made a graph here, you got 3 out of 3. All right. So don't overthink these graphs. They're usually pretty straightforward. Now, moving on to the back side, it says draw a best fit line through the data. So you get another point here for drawing a best fit line through this data set. Now, I don't have a straight edge with me right now, so I'm just going to have to freehand this. But some of you guys had really, really rough lines of best fit. So make sure when you do these, you're doing a nice job on them. That's not the best.
Staff, Johnston Controls is waiting for you outside of the bus alley door.
Sorry for this interruption. All right, draw best fit line through the data. We got 1 point for doing that right there. So now we move on to the second part. Use the best fit line to obtain the mass of the glider. All right, now let's look at our conservation of energy equation we had here. It was 1/2 mv squared is equal to 1/2 40 times x squared. That is what we're going to use to help us figure out this best fit line. So write this out. I've got 1/2 mv squared is equal to 1/2 kx squared. So these are going to cancel. Now I got to think, I want to get this into y equals mx plus b form. And what did I put on my y-axis? Well, I put v squared on the y-axis and I put x squared on the x-axis. So let's arrange it as such. I got v squared is equal to k over m times x squared. So here's my y value, here's my m value, and here's my x value, which means that k over m is equal to my slope. All right. Now, slope is calculated as the change of y over the change of x. This requires 2 points. Those points need to come from your best fit line. So you need to go back to your best fit line, which mine's not that great, and select 2 points that are on that line. All right, 2 points that are on the best fit line. So I already picked some points. We'll go ahead and write these out. I had the change of y is going to be equal to 4.8 minus 1.0, and that's meters squared per second squared, all over the change of x, which is 2.4 minus 0.5, which that's times 10 to the minus 2 meters squared. So this is going to give me 2.0 times 10 squared seconds to the minus 2. Now I'm going to set that slope equal to k over m. So I'm going to say 2.0 times 10 squared seconds to the minus 2 is equal to k over m, which means m is going to be equal to 40 divided by 2.0 times 10 squared. So m is equal to 0.20 kg. Now, this had a range of 0.18 to 0.22. So if you're within that range, you got the points there. On this one, where your points came from, you had 1 for the best fit line and then 3 for this. So you had 3 for recognizing, for using 2 points for the slope. Then you had 1 for recognizing what the slope is equal to. So that slope is equal to k over m. And then 1 for the correct answer. All right. Now on to this last part. This last part is deceivingly, it seems real easy, but it is more complex than it might let on. This right here is where things get a little fishy. All right. So looking at this, most of us got the fact that there's potential energy due to gravity, there's potential energy due to the spring, and there's kinetic energy present here. How we represented the potential energy due to gravity, though, is where we got a little bit messed up, all right? So what we need to do is read in this part D. It says the track is tilted at an angle theta, and when the spring is unstretched, the center of the glider is at a height h, all right? So that means that when potential energy due to gravity is equal to mgh, potential energy in the spring is 0, all right? Any other value away from h, however, we have a potential energy in the spring, because that means the spring is going to be stretched or compressed. So let's figure out how we can represent that. We've got this length x here. I'm going to zoom in on this part. We've got this length x there, and then we have this angle theta. Now this angle theta is pretty much like, let's see where to represent this. This angle theta is right about here. All right. So we want to figure out how much height x adds. If I displace the mass this length x, how much height does that give me? All right. So if I look at this, it's going to go about this much higher. All right. So here's my length x. So I need to figure out what is that height right there. Well, here's theta. I know what the hypotenuse is. It's x. So that height is going to be x sine of theta. So really, my final height is equal to h plus x sine of theta. So recognizing this, recognizing that displacing the spring from a height h is going to change the overall height, that is worth 2 points on this problem. All right, so this little statement right there is pretty much worth 2 points. And then what we end up getting, if we get our conservation of kinetic energy, remember that's, or conservation of energy, that's going to be that the change of energy is 0 here. My kinetic energy is going to be equal to my potential energy in my spring plus my potential energy in my due to gravity, which means that 1/2 mv squared is going to be equal to 1/2 kx squared plus mgh. Now h is equal to that right there, h plus x sine of theta, because I need to account for how much it's been displaced by. This was a tough problem. All right, there were 4 points available here. You got 2 for recognizing the difference in the height, and then 1 for getting this whole entire equation correct. All right, will the graph of v squared versus x squared for this new experiment be a straight line? All right, the answer here is no, because v squared will vary with x squared and x. All right, before it was just these 2 terms, but now I've got this term here as well with another x in it. All right, if this was just simply a constant, then we'd be fine. But because there's an x there, we're going to have some different things. All right, and again, there were 2 points here. 1 point for this, for the correct answer, and then 1 point for the correct justification.